Welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster. Today's episode is from a Wikipedia article titled Solar System. The solar system is the gravitational bound system of the sun and the objects that orbit it, either directly or indirectly. Of the objects that orbit the sun directly, the largest are the 8 planets, with the remainder being smaller objects, the dwarf planets and small solar system bodies. Of the objects that orbit the sun indirectly, the natural satellites, 2 are larger than the smallest planet, Mercury. The solar system formed 4.6 billion years ago from the gravitational collapse of a giant interstellar molecular cloud. The vast majority of the system's mass is in the Sun, with the majority of the remaining mass contained in Jupiter. The 4 smaller inner system planets, Mercury, Venus, Earth, and Mars, are terrestrial planets, being primarily composed of rock and metal. The 4 outer system planets are giant planets, being substantially more massive than the terrestrials. The 2 largest planets, Jupiter and Saturn, are gas planets, being composed mainly of hydrogen and helium. The 2 outermost planets, Uranus and Neptune, are ice giants, being composed mostly of substances with relatively high melting points, compared with hydrogen and helium, called volatiles, such as water, ammonia, and methane. All 8 planets have almost circular orbits that lie within a nearly flat disk called the ecliptic. The solar system also contains smaller objects. The asteroid belt, which lies between the orbits of Mars and Jupiter, mostly contains objects composed like the terrestrial planets of rock and metal. Beyond Neptune's orbit lie the Kuiper belt and scattered disk, which are populations of trans-Neptunian objects, composed mostly of ices, and beyond them a newly discovered population of sednoids. Within these populations, some objects are large enough to have rounded under their own gravity, though there is considerable debate as to how many there will prove to be. Such objects are categorized as dwarf planets. The only certain dwarf planet is Pluto, with another trans-Neptunian object, Ares, expected to be, and the asteroid Ceres at least close to being a dwarf planet. In addition to these 2 giants, various other small body populations, including comets, centaurs, and interplanetary dust clouds, freely travel between regions. 6 of the planets, the 6 largest possible dwarf planets, and many of the smaller bodies are orbited by natural satellites, usually termed moons after the moon. Each of the outer planets is encircled by planetary rings of dust and other small objects. The solar wind, a stream of charged particles flowing outwards from the sun, creates a bubble-like region in the interstellar medium known as the heliosphere. The heliopause is the point at which pressure from the solar wind is equal to the opposing pressure of the interstellar medium. It extends out to the edge of the scattered disk. The Oort cloud, which is thought to be the source for long-period comets, may also exist at a distance roughly 1,000 times further than the heliosphere. The solar system is located 26,000 light-years from the center of the Milky Way galaxy in the Orion Arm, which contains most of the visible stars in the night sky. The nearest stars are within the so-called local bubble, with the closest Proxima Centauri at 4.25 light-years. Discovery and exploration. For most of history, humanity did not recognize or understand the concept of the solar system. Most people up to the late Middle Ages, Renaissance, believed Earth to be stationary at the center of the universe and categorically different from the divine or ethereal objects that move through the sky. Although the Greek philosopher Aristarchus of Samos had speculated on a heliocentric reordering of the cosmos, Nicolaus Copernicus was the first to develop a mathematically predictive heliocentric system. In the 17th century, Galileo discovered that the sun was marked with sunspots and that Jupiter had 4 satellites in orbit around it. Christian Huygens followed on from Galileo's discoveries by discovering Saturn's moon Titan and the shape of the rings of Saturn. Around 1677, Edmund Halley observed a transit of Mercury across the sun, leading him to realize that observations of the solar parallax of a planet, more ideally using the transit of Venus, could be used to trigonometrically determine the distances between Earth, Venus, and the Sun. In 1705, Halley realized that repeated sightings of a comet were of the same object, returning regularly once every 75 to 76 years. This was the first evidence that anything other than the planets orbited the Sun, though this had been theorized about comets in the 1st century by Seneca. Around 1704, the term solar system first appeared in English. In 1838, Frederick Bessel successfully measured a stellar parallax, an apparent shift in the position of a star created by Earth's motion around the Sun, providing the first direct experimental proof of heliocentrism. Improvements in observational astronomy and the use of uncrewed spacecraft have since enabled the detailed investigation of other bodies orbiting the Sun. Structure and composition. The principal component of the solar system is the Sun, a G2 main sequence star that contains 99.86% of the system's known mass and dominates it gravitationally. The Sun's 4 largest orbiting bodies, the giant planets, account for 99% of the remaining mass, with Jupiter and Saturn together comprising more than 90%. The remaining objects of the solar system, including the 4 terrestrial planets, the dwarf planets, moons, asteroids, and comets, together comprise less than 0.002% of the solar system's total mass. Most large objects in orbit around the Sun lie near the plane of Earth's orbit, known as the ecliptic. The planets are very close to the ecliptic, whereas comets and Kuiper belt objects are frequently at significantly greater angles to it. As a result of the formation of the solar system, planets and most other objects orbit the Sun in the same direction that the Sun is rotating, counterclockwise, as viewed from above Earth's North Pole. There are exceptions, such as Halley's Comet. Most of the larger moons orbit their planets in this prograde direction, with Titan being the largest retrograde exception, and most larger objects rotate themselves in the same direction, with Venus being a notable retrograde exception. The overall structure of the charted regions of the solar system consists of the Sun, 4 relatively small inner planets surrounded by a belt of mostly rocky asteroids, and 4 giant planets surrounded by the Kuiper Belt of mostly icy objects. Astronomers sometimes informally divide this structure into separate regions. The inner solar system includes the 4 terrestrial planets and the asteroid belt. The outer solar system is beyond the asteroids, including the 4 giant planets. Since the discovery of the Kuiper Belt, the outermost parts of the solar system are considered a distinct region, consisting of the objects beyond Neptune. Most of the planets in the solar system have secondary systems of their own, being orbited by planetary objects called natural satellites or moons, 2 of which, Titan and Ganymede, are larger than the planet Mercury. The 4 giant planets have planetary rings, thin bands of tiny particles that orbit them in unison. Most of the largest natural satellites are in synchronous rotation, with one face permanently turned toward their parent. Kepler's laws of planetary motion describe the orbits of objects about the Sun. Following Kepler's laws, each object travels along an ellipse with the Sun at one focus. Objects closer to the Sun with smaller semi-major axes travel more quickly because they are more affected by the Sun's gravity. On an elliptical orbit, a body's distance from the Sun varies over the course of its year. A body's closest approach to the Sun is called its perihelion, whereas its most distant point from the Sun is called its aphelion. The orbits of the planets are nearly circular, but many comets, asteroids, and Kuiper Belt objects follow highly elliptical orbits. The positions of the bodies of the solar system can be predicted using numerical models. Although the Sun dominates the system by mass, it accounts for only about 2% of the angular momentum. The planets dominated by Jupiter account for most of the rest of the angular momentum due to the combination of their mass, orbit, and distance from the Sun, with a possibly significant contribution from comets. The Sun, which comprises nearly all the matter in the solar system, is composed of roughly 98% hydrogen and helium. Jupiter and Saturn, which comprise nearly all the remaining matter, are also primarily composed of hydrogen and helium. A composition gradient exists in the solar system, created by heat and light pressure from the Sun. Those objects closer to the Sun, which are more affected by heat and light pressure, and composed of elements with high melting points. Objects farther from the Sun are composed largely of materials with lower melting points. The boundary in the solar system beyond which those volatile substances could condense is known as the frost line, and it lies at roughly 5 AU from the Sun. The objects of the inner solar system are composed mostly of rock, the collective name for compounds with high melting points, such as silicates, iron, or nickel, that remain solid under almost all conditions in the protoplanetary nebula. Jupiter and Saturn are composed mainly of gases, the astronomical term for materials with extremely low melting points and high vapor pressure, such as hydrogen, helium, and neon, which were always in the gaseous phase in the nebula. Ices like water, methane, ammonia, hydrogen sulfide, and carbon dioxide have melting points up to a few hundred kelvins. This can be found as ices, liquids, or gases in various places in the solar system, whereas in the nebula they were either in the solid or gaseous phase. Icy substances comprise the majority of the satellites of the giant planets. as well as most of Uranus and Neptune, the so-called ice giants, and the numerous small objects that lie beyond Neptune's orbit. Together, gases and ices are referred to as volatiles. Distances and scales. The distance from Earth to the Sun is 1 astronomical unit, AU, 150 million kilometers, 93 million miles. For comparison, the radius of the Sun is 0.0047 astronomical units. Thus, the Sun occupies 0.00001% of the volume of a sphere, with a radius the size of Earth's orbit, whereas Earth's volume is roughly 1/1,000,000th that of the Sun. Jupiter, the largest planet, is 5.2 astronomical units from the Sun and has a radius of 71,000 kilometers, whereas the most distant planet Neptune is 30 astronomical units from the Sun. With a few exceptions, the farther a planet or belt is from the Sun, the larger the distance between its orbit and the orbit of the next nearer object to the Sun. For example, Venus is approximately 0.33 astronomical units farther out from the Sun than Mercury, whereas Saturn is 4.3 astronomical units out from Jupiter, and Neptune lies 10.5 astronomical units out from Uranus. Attempts have been made to determine a relationship between these orbital distances, but no such theory has been accepted. Some solar system models attempt to convey the relative scales involved in the solar system on human terms. Some are small in scale and may be mechanical, called orreries, whereas others extend across cities or regional areas. The largest such scale model, the Sweden solar system, uses the 10-meter Ericsson globe in Stockholm as its substitute sun, and following the scale, Jupiter is a 7.5-meter sphere at Stockholm Arlanda Airport, 40 kilometers away, whereas the farthest current object, Sedna, is a 10-centimeter sphere in Luleå, 912 kilometers away. If the Sun-Neptune distance is scaled to 100 meters, then the Sun would be about 3 centimeters in diameter, roughly 2/3 the diameter of a golf ball. The giant planets would be all smaller than about 3 millimeters, and Earth's diameter, along with that of the other terrestrial planets, would be smaller than a flea at that scale. Formation and evolution. The solar system formed 4.568 billion years ago from the gravitational collapse of a region within a large molecular cloud. This initial cloud was likely several light years across and probably birthed several stars. As is typical of molecular clouds, this one consisted mostly of hydrogen with some helium and small amounts of heavier elements fused by previous generations of stars. As the region that would become the solar system known as the pre-solar nebula collapsed, conservation of angular momentum caused it to rotate faster. The center, where most of the mass collected, became increasingly hotter than the surrounding disk. As the contrasting nebula rotated faster, it began to flatten into a protoplanetary disk with a diameter of roughly 200 astronomical units and a hot, dense protostar at the center. The planets formed by accretion from this disk, in which dust and gas gravitationally attracted each other, coalescing to form ever larger bodies. Hundreds of protoplanets may have existed in the early solar system, but they either merged or were destroyed, leaving the planets, dwarf planets, and leftover minor bodies. Due to their higher boiling points, Only metals and silicates could exist in solid form in the warm inner solar system close to the Sun, and these would eventually form the rocky planets of Mercury, Venus, Earth, and Mars. Because metallic elements only comprised a very small fraction of the solar nebula, the terrestrial planets could not grow very large. The giant planets, Jupiter, Saturn, Uranus, and Neptune, formed further out beyond the frost line, the point between the orbits of Mars and Jupiter, where material is cool enough for volatile icy compounds to remain solid. The ices that formed these planets were more plentiful than the metals and silicates that formed the terrestrial inner planets, allowing them to grow massive enough to capture large atmospheres of hydrogen and helium, the lightest and most abundant elements. Leftover debris that never became planets congregated in regions such as the asteroid belt, Kuiper belt, and Oort cloud. The NICE model is an explanation for the creation of these regions and how the outer planets could have formed in different positions and migrated to their current orbits through various gravitational interactions. Within 50 million years, the pressure and density of hydrogen in the center of the protostar became great enough for it to begin thermonuclear fusion. The temperature, reaction rate, pressure, and density increased until hydrostatic equilibrium was achieved. The thermal pressure equaled the force of gravity. At this point, the Sun became a main sequence star. The main sequence phase from beginning to end will last about 10 billion years for the Sun compared to around 2 billion years for all other phases of the Sun's pre-remnant life combined. Solar wind from the Sun created the heliosphere and swept away the remaining gas and dust from the protoplanetary disk into interstellar space, ending the planetary formation process. The Sun is growing brighter. Early in its main sequence life, its brightness was 70% that of what is today. The solar system will remain roughly as we know it today until the hydrogen in the core of the Sun has been entirely converted to helium, which will occur roughly 5 billion years from now. This will mark the end of the Sun's main sequence life. At that time, the core of the Sun will contract with hydrogen fusion occurring along a shell surrounding the inert helium, and the energy output will be much greater than at present. The outer layers of the Sun will expand to roughly 260 times its current diameter, and the Sun will become a red giant. Because of its vastly increased surface area, the surface of the Sun will be considerably cooler than it is on the main sequence. The expanding Sun is expected to vaporize Mercury and render Earth uninhabitable. Eventually, the core will be hot enough for helium fusion. The Sun will burn helium for a fraction of the time it burned hydrogen in the core. The Sun is not massive enough to commence the fusion of heavier elements, and nuclear reactions in the core will dwindle. Its outer layers will move away into space, leaving a white dwarf, an extraordinarily dense object half the original mass of the Sun, but only the size of Earth. The ejected outer layers will form what is known as a planetary nebula, returning some of the material that formed the Sun, but now enriched with heavier elements like carbon, to the interstellar medium. Sun. The Sun is the solar system's star, and by far its most massive component. Its large mass, which comprises 99.86% of all the mass in the solar system, produces temperatures and densities in its core high enough to sustain nuclear fusion of hydrogen into helium, making it a main sequence star. This releases an enormous amount of energy, mostly radiated into space as electromagnetic radiation, peaking in visible light. The Sun is a G2 type main sequence star. Hotter main sequence stars are more luminous. The Sun's temperature is intermediate between that of the hottest stars and that of the coolest stars. Stars brighter and hotter than the Sun are rare, whereas substantially dimmer and cooler stars, known as red dwarfs, make up 85% of the stars in the Milky Way. The Sun is a population 1 star. It has a higher abundance of elements heavier than hydrogen and helium, metals in astronomical parlance, than the older population 2 stars. Elements heavier than hydrogen and helium were formed in the cores of ancient and exploding stars. So the first generation of stars had to die before the universe could be enriched with these atoms. The oldest stars contain few metals, whereas stars born later have more. This high metallicity is thought to have been crucial to the Sun's development of a planetary system, because the planets form from the accretion of metals. Interplanetary medium. The vast majority of the solar system consists of a near vacuum known as the interplanetary medium. Along with light, the Sun radiates a continuous stream of charged particles, a plasma, known as the solar wind. This stream of particles spreads outwards at roughly 1.5 million kilometers per hour, creating a tenuous atmosphere that permeates the interplanetary medium out to at least 100 astronomical units. Activity on the Sun's surface, such as solar flares and coronal mass ejections, disturbs the heliosphere, creating space weather and causing geometric storms. The largest structure within the heliosphere is the heliospheric current sheet, a spiral form created by the actions of the Sun's rotating magnetic field on the interplanetary medium. Earth's magnetic field stops its atmosphere from being stripped away by the solar wind. Venus and Mars do not have magnetic fields, and as a result, the solar wind is causing their atmospheres to gradually bleed away into space. Coronal mass ejections and similar events blow a magnetic field and huge quantities of material from the surface of the Sun. The interaction of this magnetic field and material with Earth's magnetic field funnels charged particles into Earth's upper atmosphere, where its interactions create aurorae seen near the magnetic poles. The heliosphere and planetary magnetic fields, for those planets that have them, partially shield the solar system from high-energy interstellar particles called cosmic rays. The density of cosmic rays in the interstellar medium and the strength of the Sun's magnetic field change on very long timescales. So the level of cosmic ray penetration in the solar system varies, though by how much is unknown. The interplanetary medium is home to at least 2 disk-like regions of cosmic dust. The first, the zodiacal dust cloud, lies in the inner solar system and causes the zodiacal light. It was largely formed by collisions within the asteroid belt, brought on by gravitational interactions with the planets. The second dust cloud extends from about 10 astronomical units to about 40 astronomical units, and was probably created by similar collisions within the Kuiper belt. Inner solar system. The inner solar system is the region comprising the terrestrial planets in the asteroid belt. Composed mainly of silicates and metals, the objects of the inner solar system are relatively close to the Sun. The radius of this entire region is less than the distance between the orbits of Jupiter and Saturn. This region is also within the frost line, which is a little less than 5 astronomical units from the Sun. Inner planets. The 4 terrestrial or inner planets have dense, rocky compositions, few or no moons, and no ring systems. They are composed largely of refractory minerals, such as the silicates, which form their crusts and mantles, and metals, such as iron and nickel, which form their cores. 3 of the 4 inner planets, Venus, Earth, and Mars, have atmospheres substantial enough to generate weather. All have impact craters and tectonic surface features, such as rift valleys and volcanoes. The term inner planet should not be confused with inferior planet, which designates those planets that are closer to the Sun than Earth is, i.e., Mercury and Venus. Mercury. Mercury is the closest planet to the Sun, and on average, all 7 other planets. The smallest planet in the solar system, Mercury has no natural satellites. Besides impact craters, its only known geological features are lobed ridges, or rupees, that were probably produced by a period of contraction early in its history. Mercury's very tenuous atmosphere consists of atoms blasted off its surface by the solar wind. Its relatively large iron core and thin mantle have not yet been adequately explained. Hypotheses include that its outer layers were stripped off by a giant impact, or that it was prevented from fully accreting by the young sun's energy. Venus. Venus is close in size to Earth, and, like Earth, has a thick silicate mantle around an iron core, a substantial atmosphere, and evidence of internal geological activity. It is much drier than Earth, and its atmosphere is 90 times as dense. Venus has no natural satellites. It is the hottest planet with surface temperatures over 400 degrees Celsius, most likely due to the amount of greenhouse gases in its atmosphere. No definitive evidence of current geological activity has been detected on Venus, but it has no magnetic field that would prevent depletion of its substantial atmosphere, which suggests that its atmosphere is being replenished by volcanic eruptions. Earth. Earth is the largest and densest of the inner planets, the only one known to have current geological activity, and the only place where life is known to exist. Its liquid hydrosphere is unique among the terrestrial planets, and it is the only planet where plate tectonics have been observed. Earth's atmosphere is radically different from those of the other planets, having been altered by the presence of life to contain 21% free oxygen. It has one natural satellite, the Moon, the only large satellite of a terrestrial planet in the solar system. Mars. Mars is smaller than Earth and Venus. It has an atmosphere of mostly carbon dioxide with a surface pressure of 6.1 millibars. Its surface, peppered with vast volcanoes such as Olympus Mons and rift valleys such as Valles Marineris, show geological activity that may have persisted until as recently as 2 million years ago. Its red color comes from iron oxide, rust, in its soil. Mars has 2 tiny natural satellites, Diomas and Phobos, thought to be either captured asteroids or ejected debris from a massive impact early in Mars history. Asteroid belt. Asteroids, except for the largest series, are classified as small solar system bodies. They're composed mainly of refractory rock and metallic minerals with some ice. They range from a few meters to hundreds of kilometers in size. Asteroids smaller than 1 meter are usually called meteoroids and micrometeoroids, grain-sized, depending on different, somewhat arbitrary definitions. The asteroid belt occupies the orbit between Mars and Jupiter, between 2.3 and 3.3 astronomical units from the Sun. It is thought to be remnants from the solar system's formation that failed to coalesce because of the gravitational interference of Jupiter. The asteroid belt contains tens of thousands, possibly millions, of objects over 1 kilometer in diameter. Despite this, the total mass of the asteroid belt is unlikely to be more than 1,000th of that of Earth. The asteroid belt is very sparsely populated. Spacecraft routinely pass through without incident. Ceres. Ceres is the largest asteroid, a protoplanet, and a dwarf planet. It has a diameter of slightly under 1,000 kilometers and a mass large enough for its own gravity to pull it into a spherical shape. Ceres was considered a planet when it was discovered in 1801 and was reclassified to asteroid in the 1850s as further observations revealed additional asteroids. It was classified as a dwarf planet in 2006 when the definition of a planet was created. Asteroid groups. Asteroids in the asteroid belt are divided into asteroid groups and families based on their orbital characteristics. Asteroid moons are asteroids that orbit larger asteroids. They are not as clearly distinguished as planetary moons, sometimes being almost as large as their partners. The asteroid belt also contains main belt comets, which may have been the source of Earth's water. Jupiter Trojans are located in either of Jupiter's L4 or L5 points, gravitationally stable regions leading and trailing a planet in its orbit. The term Trojan is also used for small bodies in an other planetary or satellite Lagrange point. Hilda asteroids are in a 2 to 3 resonance with Jupiter. That is, they go around the Sun 3 times for every 2 Jupiter orbits. The inner solar system also contains near-Earth asteroids, many of which cross the orbits of the inner planets. Some of them are potentially hazardous objects. Outer solar system. The outer region of the solar system is home to the giant planets and their large moons. The centaurs and many short-period comets also orbit in this region. Due to their greater distance from the Sun, the solid objects in the outer solar system contain a high proportion of volatiles, such as water, ammonia, and methane, than those of the inner solar system because the lower temperatures allow these compounds to remain solid. Outer planets. The 4 outer planets, or giant planets, sometimes called Jovian planets, collectively make up 99% of the mass known to orbit the Sun. Jupiter and Saturn are together more than 400 times the mass of Earth and consist overwhelmingly of the gases hydrogen and helium, hence their designation as gas giants. Uranus and Neptune are far less massive, less than 20 Earth masses each, and are composed primarily of ices. For these reasons, some astronomers suggest they belong in their own category, ice giants. All four giant planets have rings, although only Saturn's ring system is easily observed from Earth. The term superior planet designates planets outside Earth's orbit and thus includes both the outer planets and Mars. Jupiter. Jupiter is 2.5 times the mass of all the other planets put together. It is composed largely of hydrogen and helium. Jupiter's strong internal heat creates semi-permanent features in its atmosphere, such as cloud bands and the Great Red Spot. Jupiter has 79 known satellites. The four largest, Ganymede, Callisto, Io, and Europa, show similarities to the terrestrial planets, such as volcanism and internal heating. Ganymede, the largest satellite in the solar system, is larger than Mercury. Saturn. Saturn, distinguished by its extensive ring system, has several similarities to Jupiter, such as its atmospheric composition and magnetosphere. Although Saturn has 60% of Jupiter's volume, it is less than a third as massive. Saturn is the only planet of the solar system that is less dense than water. The rings of Saturn are made up of small ice and rock particles. Saturn has 82 confirmed satellites composed largely of ice. Two of these, Titan and Enceladus, show signs of geological activity. Titan, the second largest moon in the solar system, is larger than Mercury and the only satellite in the solar system with a substantial atmosphere. Uranus. Uranus is the lightest of the outer planets. Uniquely among the planets, it orbits the Sun on its side. Its axial tilt is over 90 degrees to the ecliptic. It has a much colder core than the other giant planets and radiates very little heat into space. Uranus has 27 known satellites, the largest ones being Titania, Oberon, Umbriel, Ariel, and Miranda. Neptune. Neptune, though slightly smaller than Uranus, is more massive and hence more dense. It radiates more internal heat, but not as much as Jupiter or Saturn. Neptune has 14 known satellites. The largest, Triton, is geologically active with geysers of liquid nitrogen. Triton is the only large satellite with a retrograde orbit. Neptune is accompanied in its orbit by several minor planets, termed Neptune Trojans, that are in one-to-one resonance with it. Centaurs. The centaurs are icy comet-like bodies whose orbits have semi-major axes greater than Jupiter's and less than Neptune's. The largest known centaur, 10199 Chariklo, has a diameter of about 250 kilometers. The first centaur discovered, 2060 Chiron, has also been classified as a comet because it develops a coma just as comets do when they approach the sun. Comets. Comets are small solar system bodies, typically only a few kilometers across, composed largely of volatile ices. They have highly eccentric orbits, generally a perihelion within the orbits of the inner planets, and an aphelion far beyond Pluto. When a comet enters the inner solar system, its proximity to the Sun causes its icy surface to sublimate and ionize, creating a coma, a long tail of gas and dust often visible to the naked eye. Short period comets have orbits lasting less than 200 years. Long period comets have orbits lasting thousands of years. Short period comets are thought to originate in the Kuiper belt, whereas long period comets, such as the Hale-Bopp, are thought to originate in the Oort cloud. Many comet groups, such as the Kreutz sungrazers, formed from the breakup of a single parent. Some comets with hyperbolic orbits may originate outside the solar system, but determining their precise orbits is difficult. Old comets whose volatiles have mostly been driven out by solar warming are often categorized as asteroids. Trans-Neptunian region. Beyond the orbit of Neptune lies the area of the trans-Neptunian region, with the donut-shaped Kuiper belt, home of Pluto and several other dwarf planets, and an overlapping disk of scattered objects, which is tilted toward the plane of the solar system and reaches much further out than the Kuiper belt. The entire region is still largely unexplored. It appears to consist overwhelmingly of many thousands of small worlds, the largest having a diameter only a fifth that of Earth, and a mass far smaller than that of the Moon, composed mainly of rock and ice. This region is sometimes described as the third zone of the solar system, enclosing the inner and the outer solar system. Kuiper belt. The Kuiper belt is a great ring of debris similar to the asteroid belt, but consisting mainly of objects composed primarily of ice. It extends between 30 and 50 astronomical units from the Sun. Though it is estimated to contain anything from dozens to thousands of dwarf planets, it is composed mainly of small solar system bodies. Many of the larger Kuiper belt objects, such as Quaoar, Varuna, and Orcus, may prove to be dwarf planets with further data. There are estimated to be over 100,000 Kuiper belt objects with a diameter greater than 50 kilometers. The total mass of the Kuiper belt is thought to be only a tenth or even a hundredth the mass of Earth. Many Kuiper belt objects have multiple satellites, and most have orbits that take them outside the plane of the ecliptic. The Kuiper belt can be roughly divided into the classical belt and the resonances. Resonances are orbits linked to that of Neptune, e.g., twice for every 3 Neptune orbits, or once for every 2. The first resonance begins within the orbit of Neptune itself. The classical belt consists of objects having no resonance with Neptune and extends from roughly 39.4 to 47.7 astronomical units. Members of the classical Kuiper belt are classified as Cubewanos, after the first of their kind to be discovered, 15760 Albion, which previously had the provisional designation 1992 QB1, and are still in near primordial low eccentricity orbits. Pluto and Charon. The dwarf planet Pluto, with an average orbit of 39 astronomical units, is the largest known object in the Kuiper belt. When discovered in 1930, it was considered to be the 9th planet. This changed in 2006 with the adoption of a formal definition of planet. Pluto has a relatively eccentric orbit, inclined 17 degrees to the ecliptic plane, and ranging from 29.7 astronomical units from the Sun at perihelion, within the orbit of Neptune, to 49.5 astronomical units at aphelion. Pluto has a 3-to-2 resonance with Neptune meaning that Pluto orbits twice round the Sun for every 3 Neptunian orbits. Kuiper Belt objects whose orbits share this resonance are called Plutinos. Charon, the largest of Pluto's moons, is sometimes described as part of a binary system with Pluto, as the two bodies orbit a barycenter of gravity above their surfaces, i.e., they appear to orbit each other. Beyond Charon, 4 smaller moons, Styx, Nix, Kerberos, and Hydra, orbit within the system.